possible. Your summer review quiz, you need to come in to work on corrections with me, right?
Yeah.
Doesn't mean like necessarily sitting at my desk, although if you come after school, I might be available. Hey, you can come to Chick-fil-A and work with me tomorrow. I think I'm getting Mrs. Regan there. Good team. Good team. Good times. However, right now, we are going to work on this thing called finding limits analytically because we have a homework due tomorrow. True? Okay, so as you guys open your flip book, where's the first page that you come to? What are the basic rules, guys? Oh my goodness! Aren't these kind of like the properties that we talked about? What's different between these basic rules and the properties that we talked about in our notes? Can you guys see the difference? There we go. What's the difference between your flip book, because you guys have the flip book right in front of you, and our basic properties? They're very similar except for one thing. Yeah. And this one in our properties, they put L's and K's because that was the way of like summarizing kind of what was going on. But in yours, they talk about it with F's and G's. They never go to the L's and K's. Does it mean the same thing though?
Yes.
Yeah, because you could technically take out this L and put in the limit as x approaches C of f of x, or take out the L and K and put in the limit and the limit. So these basic rules are basically what we already have written down, but in a little bit more proper form for the AP. Now you guys could totally like be doodling and making it look cute and like putting stars by things that are important, etc., etc. But what do you have underneath the basic rules? Limits at infinity. Now, wait a minute. What's going on here? Limits at infinity. Hold on. We talked about yesterday a limit to infinity, right? Because that was in the example. What do we need to think about when we're going to infinity? When we have x approaching positive infinity. Oh, struggle. My pen just decided to die. Oh, my book's all messed up now. Anybody else feeling my pain? That's very sad. It's okay. We can do this instead. Okay. This is not a graphically or doing limits graphically notebook, but couldn't we put some reminders? Like, if x is going to infinity, what direction are we thinking about with the graph, guys? To the right. Good. So we can put to the right. Now, what if we have x approaching negative infinity? To the left. However, that's when we're going to infinities, right? To the right or to the left when we're looking at all of these ones down below. So to the right, to the left. But up here when we were approaching a constant, what happens if we see x approaching a with a little negative? What should we be thinking? It's easier to say from. I think it's easier to say from with these. From below. From below, from the left of a, right? And if we have x approaching a positive, what should we be thinking? From above. So those are just some quick little like reminders. And why am I saying that? Because down here with limits at infinity, guys, should you know or should you be memorizing the graph of e to the x? Yes, because doesn't the graph of e to the x, doesn't it look like a little baby? Swoop, there it is, right? So what happens as our e to the x swoops to the right? Where does he go? And what happens as our e to the x swoops to the left if you were to draw your little graph? Remember the basic graphs from Forever Card 1? Where is e to the x going to the left? 0. Now hold on, what does ln look like? He's a swoop but the other way, right? Because he's the inverse of e, so wouldn't he swoop this way? So what's going on as as x goes to infinity? Infinity. Slower, but still infinity. But wait a minute, why isn't x going to negative infinity? I don't get it. Because ln can't pass what? The vertical asymptote. Remember, ln has a domain problem. Its argument has to stay greater than 0. So x can only approach 0 from above, right? And then where is ln going? Got it. Now we also have c over x to the r. And that's a kind of weird one unless you realize that that could be something depending on what my power is. Like those ones with little vertical asymptotes and horizontal asymptotes. But either way, whether it's one of those where R is even or R is odd, it's going to look like either 1 over x or 1 over x squared. But either one, whether R is even or R is odd, what's going on as x approaches negative infinity? Where's this guy going? As I go to the left for either one. I know one's coming from above and one's coming from below as far as like the y values, but aren't they both going to a horizontal asymptote at 0? Right? And then technically it doesn't just have to be x approaching negative infinity, it can also be x approaching positive infinity, which is weird that they didn't show that. I'm going to put a little plus or minus. Whether you're going to the left or to the right, to the left or to the right, my function, whenever it's of this form, will be going to 0. That's a little typo. It should be a plus or minus. And then we have like a little polynomial, what's going to be happening, a little polynomial, what's going to be happening. And this has to do with n behavior as to whether it's going up, up, or down, down, or down, up. But anyway, we can talk more about this. These are limits to infinity. Just some little quick hints. But what's going on down here? If I were you, I'd be like highlighting, starring, making this kind of fun. Have you guys seen these yet? Adam? Nope, not yet. However, if you go very far in homework, you're going to come up against weird things like this. Why are these necessary? Guys, what happens if you plug 0 into sine of x over x? 0 over 0. Wait a minute! 0 over 0 yesterday. Hold on, 0 over 0 yesterday. What did it say to do? Keep going. How? Oh, we divide, we rationalize, we simplify. Wait, we can only do that when we have polynomials. Which in the examples you guys saw at the beginning of class, didn't we have a conjugate one? Or a complex fraction one? Or a factoring? Oh, that's in factor. Factoring? Oh, that's in factor. Okay, well, I didn't give you a factoring one. But these are ones that you can have different procedures for keeping going. However, wait a minute, what about this dude? How do you keep going if you have a sine? Ugh. Cancel out the x's and have sin? No, let's not have sin. That's not something we should be wanting, right? It happens naturally. We are broken, depraved people, but we don't go chasing after it or trying to get it. You can't just cross off x and have sin. That's not going to mean anything. So therefore, there are snazzy geometric proofs as to why this is true, but we're not going to worry about geometric proofs. We're just going to, for our purposes, memorize these special limits. We're just going to memorize these special limits. And so in your notes, actually, it was coming a little bit in the future, but that's totally okay. We can do it now. Boop-boop. For transcendental functions, trig, exponential, logarithmic, we are going to simplify with properties, if possible, from forever card number 1, like trig properties, like tangent equals sine over cosine, or sine squared equals 1 minus cosine squared, kind of like the teacher. We are going to simplify, if possible. We are going to need to think about things like the trigonometric identities or trigonometric properties. We'll simplify if possible. But if not possible, we need to realize that there are these special limits for trig and kind of involving exponentials with this weird 1 over x dude that we're just going to memorize. So, special limits. Hey, there's a yellow box, and every time there's a yellow box, what does that mean? It's a forever card. Forever number 3, special limits. So you guys have it in your flip book, but you're also going to make a forever card out of it. In our notes, we're just going to say, you know what, Step 1, direct substitution. Step 2, something goes wrong. 0 over 0, number over 0. With polynomial expressions, or radical expressions, or complex fractions, we can do stuff. With trig and with exponential, well, we can play with it, maybe. But if we can't play with it to get rid of the trig, if we can't plug it in, and if we're getting 0 over 0, we keep going with our special limits. And if you guys notice, in your flip book, doesn't it say sine of x over x? You can double check real quick. Isn't it the limit as x goes to 0 of sine of x over x? But what do I have that's different in your forever card? Sine of u over u. So what does that mean? Can I give you a quick example different than your flip book before we go back? Write down this forever card, but then I want you to ponder. Oops, no. X minus 2. I want you to ponder this example after you finish writing your forever card. Yeah. Yeah. Special limits. And if you want to like give yourself a little reminder so that when you're quizzing, you can put like with sine, with cosine. You can say with e. That one's hard because you're kind of going backwards. E is the answer. This is a weird one. So ponder this example. The limit as x approaches 2 of sine of x minus 2 all over x minus 2. From yesterday, the very first thing we always try with any limit would be to... Yeah, plug it in, plug it in. But what happens when you substitute? Now we can't say equals 0 over 0. Remember, that means DNE, and we have to keep going. But, I know some of you really just want to get rid of x minus 2's, but if you do that, you're left with sin. Stop. Illegal. Illegal. It's sine of. The x minus 2 is stuck in the sign. You can't just randomly cross it out. Just think you'd be left with sin. So, if I can't cross it out, and it's 0 over 0, the flip book says, cool, if you have a limit as x goes to 0, sine of x over x, it equals 1. The problem is, I don't have that. So, does my rule apply? Yes or no? Why are you saying no? That's what most people would say. Why would most people say no? What's different, obviously, like looking at it real quick? There's a 2, not a 0, right? But wait a minute. Can we take a second and say, okay, so what if u equals x minus 2? Because we're trying to make it fit this rule, right? Then wouldn't we have the limit as x minus 2 approaches 0 of sine of u over u? I could replace with u, right? I could replace with u. And if u approaches 0, wait a minute, hold on. For x minus 2 to approach 0, what needs to happen? What does x need to be approaching? Yeah. So if you were thinking about u sub, it's not necessarily that you need to show that work, but for your brain to understand, this is a u going to 0. Because x minus 2 going to 0, you could add the 2 to the other side. As x goes to 2, 2 minus 2 will go to 0. So the cool thing is, this actually is just a limit as u goes to 0. As x goes to 2, you can plug it in. U goes to 0, sine of u over u. So what can I just, because of this card, what can I say? Equals 1. So my card is built for harder problems where it's not just sine of x over x, but they could have it look a lot differently, and yet the exact same principle applies. Does that kind of make sense? You can do the same thing with 1 minus cosine of u all over u. Okay, with this, I'm just getting to more examples, and they involve trig, so I'm going to go ahead and go back in the notes if they allow me. Let's go to our flip book. Because there are some examples from the beginning of class that we weren't too solid on, and then I have even more examples. We better finish our flip book, the one that we're going to refer to whenever we get stuck with limits for the entire year, okay? So, going back to our flip book. So we have all of our basic rules. We have some reminders about limits at infinity. We have special limits. When you flip, this is what I was talking about. Ha-ha! Do we have some examples?
Yeah.
Yes, we do. Yes, we do. What do you see about this very first one? If f is a continuous function at a, plug it in, plug it in. So what did they do to solve this guy? Plug it in, plug it in. So what are we going to do for this guy? Plug it in, plug it in. So go for it, guys. What would be the final answer to number 1's limit? So we could do the square root of 7 plus 2 minus 2, which is the square root of 9, which is 3, and 3 minus 2 is 1. Sometimes it's as easy as plugging in. True? True. But what's going on with number 2? Yeah, because in the beginning, isn't this technically a 0 over 0 keep going if you were to go through all the work, right? So then they go ahead and factor, and when you factor, what are you able to do with the x minus 3's? Reduce. And when you reduce the x minus 3's, you're left with x minus 4 over x, to which, or at which point, what can you do with my limit? Plug it in, done. So, what's going on over here? Oof. There's a lot of adjusting. Let's see if this helps. Stop focusing. Yeah, 0 over 0. So how do we factor the numerator, cool kids? Good. X plus 11. X minus 2. How can I factor the denominator? X minus 2, X plus 2. What can I do with the X minus 2's? Ah! Canceling means they go to 0. Reducing means it goes to 1. Reduce. And what can I do to save a little bit of time at this point? Yeah, plug it in, plug it in. So 2 plus 11 would be 13, and 2 plus 2 is 4. Yeah?
Yeah.
But I wasn't super scared about you guys being able to do something like this with factoring because factoring is a little more normal than this next example. What's going on in this next one? Yep, and what did we talk about yesterday with rationalizing the numerator? We multiply by the, if I were you, I'd put a little hint down there, multiply by the conjugate. But what is the conjugate? Check out the example. Is this another 0 over 0 example? Yes. Since it's 0 over 0, we keep going. Now, some of you might be able to factor, but others of you, it would be easier just to multiply by the, do you see the conjugate? We're multiplying by 1 creatively. That's what's going on right here. You can even label this with what's going on. We're taking the radical expression, square root of x minus 2. And we're multiplying by the exact same binomial, but with the opposite sign. That's what a conjugate is defined to be. Now, how did they go so quickly? It's kind of like a CalcChat answer. How did they go so quickly from root x minus 2 times root x plus 2 to x minus 4? What? How'd they do that? On the bottom. How do you multiply binomials? FOIL. And when you FOIL, wouldn't you have to do first, what's root x squared? Just x. Outer would be plus 2 root x. Inner would be minus 2 root x. Oh, they're differences of squares. Those cancel. And then what's left? Minus 4. So they did FOIL, but it's a difference of squares. And so technically, a minus b times a plus b is a squared minus b squared. Or the outer and the inner cancel. But either way, we have x minus 4. What did you notice about the denominator? They left it. Why? What can you do now? Yeah, reduce, not cancel, right? We can reduce, and anytime you reduce, what is left? A 1. Plug it in, square root of 4 is 2, and 2 plus 2 is 4. So what are you going to do on this guy? Well, first plug it in, but what do you get? Okay. So since it's 0 over 0, keep going. What are we going to multiply by? You guys, lead the way. Who is the conjugate in this one?
Radical x plus 4.
Radical x plus 4. But we need to multiply by 1 creatively, which means square root of x plus 4 on top and square root of x plus 4 on bottom. True? Okay, use your example. What's going to go next? Ah, but not before you write the limit as x approaches 16, my little illegal ones. You have to rewrite the limit over and over and over again until we're able to plug in. But yes, we're foiling the top. It's a difference of squares. Do you guys see where it's going to go after we do first outer inner list? X minus 16. And on the bottom, why am I not going to multiply? Because what am I hoping to be able to do? Reduce. Good terminology. When you reduce, what is left on top? So you could rewrite it if you really want to be cool and copy the example. 1 over root x plus 4. But at the end of the day, we're able to say equals. Do you guys see how there's not really an equals before that? They're just rewriting. Now you could put equals. It's not totally wrong. But here is where we're actually solving. Equals. What do I get? Dun, 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 dun. Dun, dun. So now, do you guys know how to do that example at the beginning of class that we were like, what would you do? What would you do? Multiply by the conjugate. And what is the conjugate? Root 3x, right? Plus 3. But we have to multiply by 1 creatively to keep it all balanced. So what's on bottom? Okay, you guys get ahead of me. I think you know what you're doing. Get ahead of me. If you didn't get to do it, or if you didn't do it at the beginning of class, now do you know how? Hopefully you factored out the numerator. Who got 1/2? Are we okay? Foiling the top, keeping the bottom, factoring the top by pulling out a 3. Then I have common factors that I can reduce. And then I plug in 3 over square root of 9 plus 3 is 3 over 6. And 3 over 6 is 1/2. Now, what's the one example they're missing? Because we go straight to trig. What's the other one that you guys might have gotten stuck on up here? complex fractions, but what would have been my hint in complex fractions, guys?
Multiply common denominator.
Yeah, multiply by a common denominator, just like we did in the pre-cal packet. So this isn't specifically in the flip book. Some of you guys might want to add to your flip book if you want. However, this was from straight out of the summer review packet, as was some of the others. I would have multiplied top and bottom by 2x, and maybe some of you, as you go through your summer review quiz corrections, maybe missed this complex fraction once. You have to work on it a little bit better, or a little bit harder. Uh-oh. Don't I have 2 and x plus 2? Oh, struggle. So it's not just 2x, huh? So let me go ahead and undo some of that, because I need to multiply by a little bit more. I need to multiply by 2 and x plus 2. Somehow I totally didn't see the x plus 2. So let me go ahead and get it here. How many of you guys did this at the beginning of class? Only a couple? Man, we really got stuff at the beginning. What happens when we distribute? The x plus 2's reduce what's left. And then the 2's reduce what's left. But did you kill a seal or did you put parentheses? And then you have 2x times x plus 2. Gotta distribute that negative. And when you distribute that negative, you get a negative x and a minus 2. Don't the 2's cancel? So then they, well, canceling to 0, then the x's are going to reduce because I have a negative x on top and I have an x on bottom. After the x's reduce and I'm left with a negative 1, I can plug it in, and get negative 1 over 2 times 2 is 4. Now guys, we do have some number over 0 examples that we didn't get to. However, let's get back to our flip book because there's a trig one. And we did get to do a number over 0 yesterday. We did get to do a number over 0 yesterday. For our warm-up tomorrow, I might kind of throw some of these examples back at you and see what you can do. But let's get back and get this trig one done. Because they gave us a hard trig one that had a lot of different stuff going on. But the long story short, if you had plugged in and done your unit circle carefully, you guys would have gotten a 0 over 0 and been like, oh no. So what they did is they said, this does not look exactly like a property. Well, wait a minute. Actually, part of it does. Part of it does. 1 minus cosine of x all over x. But if you tried to separate and see what was left, eventually, if you notice, they get down to where they separate everything out to where they can actually plug in some properties. So they use some multiplying by conjugates to get a Pythagorean that they can substitute. Then they separate the signs and they separate the x's. So you can kind of separate the multiplication to see some of those special trig properties, because once they got here, he was able to become 1 because of the special trig limit. He was able to become 1. And then all of a sudden, these weren't over 0. These were actual values, so they were able to finish the problem. But as you come over here, if you plug in, you get 0 over 0 again. Does anybody have any ideas as to how to tackle this guy? Yeah, kind of. My hint would be, I would love for my cosines and sines to somehow get to be friends. And for that to happen, I think I'm going to have to multiply by the conjugate. So conjugates aren't always for radicals. They can also be with trig. Because if you multiply by conjugates, then you get cosine squareds and sine squareds. And when you have cosine squareds and sine squareds, you can use some of those cool Pythagorean properties. Do you guys see what my next step would be as I'm about to let you go? What's cosine squared of x minus 1? Careful. The signs are flipped, so it would actually be negative sine squared, but how does that make a big difference? What can you do with the sign on top and the sign on bottom? Yeah, you can, and I think that reducing is the key. All right, cool kids, this homework I want you to fully attempt for tomorrow. You're going to have some simple plug-in. You're going to have some 0 over 0s. You're going to have some trig, but probably not as hard as the crazy ones on the board. We'll finish our flip book tomorrow and see if we can put any more hints down before we move away from section 1.3. But have your homework will be attempted for tomorrow. Sound good? All right. Adios, au revoir. I'll be the same. Happy Tuesday. Chick-fil-A tomorrow.